learn about those today. But these are protons, neutrons, and electrons. These don't have characteristics of matter. They behave slightly differently. If you decide to take 101, we have a whole chapter devoted to the behavior of electrons because they are just funky in their own way. Huh?
They're weird.
Yeah, they're very weird. So when we say atom, that's going to be the smallest unit, where it still retains properties of matter. Yes, you have smaller particles, but they don't have those similar characteristics. When we look at the periodic table, now it says there's 91 different elements in nature. If you look on the periodic table, we have 118. So when you look at a periodic table, you'll notice that there's 2 rows that are actually embedded right here. They're just taken out and moved down here. Now, so we have 118 elements, but 91 are found in nature, naturally. The rest are man-made. When you look at this periodic table, if it's filled in like this, that means it's solid at room temperature. When it's blue like this or like this, it's liquid at room temperature. Notice mercury, liquid at room temperature. If it's red, that means it's gas at room temperature. And if it's not bolded, that means they don't have enough information to actually dictate what state of matter it is. And a lot of these are man-made. So a lot of them, they're not, it's not stable enough to actually figure out what its state of matter is over a long period of time. So you can see that here. We'll go through each color, why they're color coordinated. You'll notice that they have specific names to them. Columns make a difference. We arrange them in a certain way. So if you look at a periodic table, it does go in numerical order, right? Starts off 1, 2, and then keeps going. You'll also notice that the number, this number in red, is also increasing. So we'll talk about that today. The blue number is increasing by 1, so you'll see that too. But the way the periodic table is arranged is it tells you a lot more information than just by looking at it and thinking, oh, it just goes in numerical order. There's a lot more information you can get from it. Okay, Dalton's atomic theory. What does the theory tell you?
That's under investigation.
Why?
Oh, it has scientific backing to it.
Yeah, but why is something happening, right? It's not describing what is going on, it's telling you why something is happening. So here, it's telling you that, okay, atoms, they're indestructible, tiny particles. That's where it's able to support the law of conservation of mass. When we look at a given element, all the atoms inside of it are the same. So if I look at carbon and look at carbon's atoms, they're going to be identical to each other. But if I look at silver's atoms, they're going to be different than carbon's. So each element has different atoms to it. Atoms come together and form compounds. And when this happens, it's always whole number ratio. So example, when you have water, it's H2O. You're not going to see something like this. Just making this up, but not even numerically right. But if you look at it, notice I have decimal places. That's not possible. It's always a whole number ratio when we look at compounds. And we'll get into this in the next chapter where you'll learn about naming. Now, when they were doing these studies, they knew about elements. They knew about the elements, they just didn't understand what they were made of. So they knew, okay, atom, but they had no idea if there was something smaller than an atom. So, J.J. Thomson, he was doing experiments, and he was using a device that's similar to, you know, the old school TVs? Well, they're not old school, but people still have them. Like box TVs, where they have an actual backing to it. It's not a plasma TV, this thing. So, when you have those TVs, if you've ever seen it, like, fused out, there's a tube that runs behind it, and it lights up the screen. So that tube is something similar to what he was doing. So he kind of, TVs were modeled based on what experiments he was doing. And with that, he was able to figure out that there was a particle that was smaller than hydrogen. So if you look on the periodic table, hydrogen is the smallest. But he figured out, okay, there's a particle smaller than that, because its mass was lower than hydrogen's. It was like 2,000 times smaller. So he said, okay, he figured out they were really small, and then he also figured out that that particle was always attracted to a positive charge. So if it's attracted to something positive, what charge does it have?
Negative.
Yeah, it was negative. So he called these electrons. Now, he was eating plum pudding. Just think of a chocolate chip cookie. He was eating plum pudding or chocolate chip cookie, and he thought about this. He thought about, okay, these electrons, they're negatively charged, right? But when we look at atoms, they're neutral. So there has to be something positive counteracting the negative. So he came up with this, where you have this sphere of positive charge, and these electrons are scattered, like the chocolate chips, and they're negative. So you have both positive and negative charges, and they're canceling each other out. And that's where we can have an atom which is neutral. Now, they had to do further tests. So you have Rutherford, which was Thomson's, one of Thomson's students. Now, he was working with alpha particles. Now, alpha particles, they're radioactive. Thomson, he was also using radioactive particles. Now, they didn't know, the extent of damage being done to them when they were doing this, because they had no idea that it was doing damage to their cells. So, alpha particles, just think of very small particles that are unstable. They're releasing energy. Just think of it like that for now. We'll talk about the radioactive part later. Now, he did the gold foil experiment. So I'm going to show you a picture of that. So he set it up like this. He had a particular source. So just think of something like X-rays. You have these particles of energy, and they're being shot at a gold foil. So this gold foil is very thin, right? Very, very thin, like paper. So based on Thomson's actual hypothesis, he was looking at these particles and he said, okay, if we have all this positive charge, right, and negative chocolate chips, the alpha particles should go through and through, no problem, because you have a mixture of negative and positive charges. The particles will go through. Now, when he did this, a lot of the particles went through, straight through. But some of them scattered where they got deflected. So they got deflected at different angles, and some even went back to the source. So this was weird. So think of his example that he used was, think of a piece of paper. This is your gold foil. It's this thin. Think of shooting a gun, shooting a bullet towards that paper, and that bullet deflects back at you. It's a thin piece of paper. Why in the world would it deflect back at you? That doesn't make sense. So then he came up with a new model. What if, instead of a positive cloud, you have a center, a nucleus that's positive, and then an electron cloud? The electrons are scattered along the actual nucleus. So you have this very dense positive center instead. So he came up with this model, and this is dense enough to cause the particles to get deflected because you have that dense area of positive charges. So this was the new model where you have the nucleus, you have positive particles here, which are called protons. That's how I abbreviate it. Then you have the electrons in the electron cloud. So they're negatively charged, so that's how I show it. Now, if you have such a dense center, do positive charges like positive charges? No, they're going to repel. So there has to be something in here to account for that. And that's where you get the neutron. It has no charge. It's just the middleman trying to keep the protons together. So it's like, come on, people, let's be friends, right? Just trying to keep everything together. So you still have a neutral atom because you have negative, positive charges, and they're equal, but you have these neutrons here to keep that nucleus intact. Now, when we get into the radioactive aspect, that's where you get into radioactivity. Some of the neutrons will actually, or the protons, will actually emit or be released when you look at radioactive elements. They're unstable, so they want to release that. So that's where you get all that energy. Now, look at the size. You have here 10 to the negative 10 meters versus 10 to the negative 14 meters. We're talking about very small distances, right? So, instead of comparing those two, it's hard to kind of put that to scale. I use this. So, imagine the stadium, the football stadium, that's your atom. So this is where you have all your electrons, right? In the center is the nucleus. Now the nucleus is the size of a fly. So see the comparison? That's how big of a comparison it is. But the nucleus makes 99.9% of the mass for an atom. So the fly is the most dense part of an atom, holding 99.9% of the mass. The electron cloud holds the volume, but no mass. It's very, very light in that sense. So you guys see the comparison? It's huge. So the nucleus is very small compared to the actual electron cloud. Today is Monday Night Football, so if you're watching, you'll think of it, oh, the stadium is like the electron cloud. I'm sure there's a fly in the stadium, right? You can think of the nucleus as the fly. Now, when you're looking at this, one of the things that a good kind of observation to make is, notice when you look at hydrogen, it has a number underneath it. that's telling its mass essentially. And we'll talk about what this number means, how it's calculated, everything like that. Now that's the number. Now it has units to it, just understand it's the mass, right? Now if you look at hydrogen, it has 1 proton. Next element in line is helium. Helium has a mass of this. Now, it's element number 2, meaning it has 2 protons. Now, this was where they were able to figure out, okay, the nucleus is the most dense part. Because if you look at this, hydrogen, 1 proton has that mass, right? If you have 2 protons, what should happen to that 1.00794?
It should double.
It should double, right?
Quadruple.
But it doesn't, yeah. It's 4 times the amount. So they knew there was something else in the nucleus that's keeping all the protons together, right? There's something neutral there, but also it's adding to the mass. So the nucleus has the protons and neutrons, and that's where you have 99.9% of the mass. So both are adding to that mass. This is just talking about charges, right? Like will repel, separate, so positive with positive hate each other, and then opposites attract, they'll be attracted to each other, and the charges, if you have equal amount of charges, they'll also cancel out. So this is just giving you that aspect. Okay, so these are the numbers. You don't need to memorize these or anything like that. Just understand, look at the actual mass. If you notice, the proton and the neutron, they're very similar in mass. Neutrons are a little bit bigger, but keep in mind it's to the -27, right? So you're dealing with very small numbers. If you look at an electron, it's still to the -27, but the first part is really small. Now, these numbers are hard to compare with each other because they're so small, right? It's not practical to do that. So what they do is they use carbon to actually be the basis for this. This is called atomic mass units. Atomic mass units. So the way this is defined is 1.6, I want to say it's something close to 1.67 to the -27 kilograms equals 1 atomic unit. Atomic mass unit. So what they're trying to do is make this really small number, convert it into something that's comparable. So about 1.67 to the -27 equals 1 atomic unit. And then you get these numbers here. Now you're able to compare these. It's a much more practical number to use. Because if we had, 1.67 to the -27 kilograms, and then quadruple that, and then times it by 8 or whatever, these numbers would be extremely small. But notice now they're much more practical. The numbers that you've dealt with, because it's like 209 and 126 and 79, right? They're not really small numbers. So we are able to convert these to numbers that are not so small and much more easier to use. Again, the charges. Now, even though protons and neutrons hold 99.9% of the mass, You can't leave electrons out. They do a lot of work. When we look at atoms, different atoms, meaning, let's say I compare carbon to gold, right? Carbon and gold have different chemical properties, and that's because their electrons are arranged differently. So electrons do a lot of work. They determine chemical properties of these particular elements. They are the ones that will be exchanged, transferred, or shared to form compounds. So when you have compounds, meaning most famous one, like water, it's made up of hydrogen and oxygen. To make water, those electrons are being shared or transferred to make water. The actual nucleus isn't doing anything. So the nucleus is like, I hold all the mass, I don't need to do anything else. So it just hangs out in the center. The electrons are doing all the work to form these compounds. So don't leave the electrons out. They do a lot of work. Protons are the ones that determine the identity of the element. So when you look at the periodic table, this number in blue in the upper right-hand corner are the number of protons. So notice, differing by just one changes if you're talking about platinum versus gold, gold versus mercury. Just by one proton, right? It makes a huge difference. Mercury compared to gold, different properties completely. So, anytime the number of protons change, you're changing the identity of the element. You have helium versus aluminum. If you look at it, they only differ by 11 protons, but it makes a huge difference. You can see that here. Differ by one, it's going to change the identity of the actual element. Now, anytime I say atom, that means it's neutral. So that means you have the same number of protons as electrons. Protons are positively charged, electrons negatively charged. So if I look at fluorine, right, it has 9 protons, that means it has 9 electrons. I'm talking about the atom. We'll get into where electrons and protons don't have to necessarily be equal to each other. That's where you get into ions. That's going to be different.
Wait, can you repeat that one more time?
So anytime I say atom, that means you have equal amounts of protons and electrons. When we start talking about ions, well, isotopes will be different. That's where they don't equal each other. And they'll have an actual charge to it. So you'll see that. We'll indicate it with the actual symbol. Now, you know about the symbols, right? You know about element symbols. The ones that you have to know are the ones that are highlighted. I posted it on Canvas. One of the things you'll notice is the first letter is always capitalized, second letter is lowercase when you look at these. Also, when you look at elements, it's not always the first 2 letters. So notice here, magnesium is Mg, not Ma. A lot of these elements, especially the precious metals, they don't have English language backgrounds to it. They have Greek, Latin, German names to it. So when they get translated in English, they're not going to necessarily have the same symbol to it. remember the ones that you need to know, those are the ones that are posted on Canvas. These are just some cool percentages to look at. Now, if you look at, this is the most abundant elements on Earth. So looking at the crust, the oceans, the atmosphere, the air, you'll notice oxygen is the highest. Now that's not coming from air, because the most dominant gas in air is what?
Nitrogen.
It's nitrogen, not oxygen, yeah.
But there are a lot of oxides.
There's a lot of oxide compounds, and one of them, notice the second element is silicone, which is neutral, because you're like, what? Silicone? Where would that be?
Sand.
Sand. Silicone dioxide is sand. You make glass out of it. So notice those two are the most dominant. Then you get into a lot of the metals, calcium. You'll see sodium is huge too, salt, that's found in the ocean. And then you have very trace amounts of these that you'll notice. Now let's look at the human body. Again, oxygen, the dominant one, not surprising. And then number 2 is carbon.
Because of carbon-based life.
Yeah, when we talk about organic compounds, right? Organic compounds are carbon-based life forms, not organic like pesticide-free. I don't mean that. I mean organic meaning carbon-based. So if you look at it, carbon is the most dominant in that sense. Then hydrogen, oxygen, nitrogen, phosphorus, sulfur. You have whole classes devoted to organic chemistry. When we look at all the compounds found on Earth, right? Even the universe, close to 95% of them are carbon-based, organic. The rest are inorganic. So in chemistry, when we start off with talking about this, we actually start off inorganic, where we get into ionic compounds. Then we get into covalent, where it's more organic based. And then you're able to take from 101, 102, then you're able to take 112, which is organic chemistry. Because this part of chemistry is much more complex. It's what?
To me, it seems similar.
Yeah, but it's completely different from the basic chemistry that's taught. The way organic chemistry is, the nomenclature is different, a lot of the properties, just how the structures arrange themselves. It's very different than what you're used to.
It's kind of crazy.
Yeah, you can spend years and years on organic chemistry. Okay, so first thing when you look at a periodic table, again notice you're increasing the number of protons by 1. Right? So you're going 1, 2, 3, 4, all the way. Now the way it's arranged, notice it's not a perfect rectangle, right? It has dips to it, it has space here, right? Then it goes up, and then it goes up again. And then you have this segment here that comes out and goes down here. So it's arranged like that for a reason. It's just not, oh, you know, it was a cool pattern or something like that. Now, when you look at this, there's 3 main categories that you can get just by looking at the periodic table. First is anything that's kind of this brown, I don't know, does it look brown to you? No. Like a, what color would that be?
Tangerine, white.
Like this tan, kind of nude color, right? If you look at that, those are all considered metals. And we'll look at the characteristics of what metals are. But you know lot of metals, think of silver, gold, platinum, right? They're hard, they are solid at room temperature. Copper, they're good conductors of heat. Then you'll notice this staircase here. Now, this staircase you'll see on every periodic table, including the one that you get during exams and quizzes. This one's not as obvious because Matt or the technician was trying to make it like, oh, it'll stand out, but I feel like the gold doesn't stand out as much. You can kind of see the blue in that, but again, this is really far away. The one I give you during exams and quizzes has that staircase. And that staircase, right there, is to help you. Okay, disappear on me. Is to help you. This staircase will separate the metals from the non-metals. And the way we use this is anything that touches the staircase, except aluminum, notice it's a nude, not purple, it's considered a semi-metal, where it's in between a metal and a non-metal, has characteristics of both. So you'll see that. And then you go into the green. The green are non-metals. So you can go and start up upper left-hand or right-hand corner. You can go from non-metals to semi-metals to metals, all the way down. Now, with these, another name for non-metals are called metalloids. So both terms are not non-metals, sorry, semi-metals. Both terms are used interchangeably. Now we'll look at the characteristics of both. So think of metals, right? Think of copper, aluminum, silver, gold. They're very good conductors of heat. So when you're looking at this, just know the basic characteristics. Just think of a metal. What can you do to it? They're good conductors of electricity and heat. So that's the first two. Electricity and thermal, they're talking about heat. Resistance, they increase with temperature. The metals tend to be shiny, right? Gold, silver, copper. When we look at hardness, this is where we get into if it's malleable and ductile. So malleable means are you able to pound it out into sheets? Can you do that with copper? Gold? Yeah, you can pound them out into sheets. Aluminum foil, right? Ductile means can you make wire out of it? So copper wire, platinum wire, expensive, but gold wire, even platinum wire is expensive. But can you make wire out of it? And then the states at room temperature, they tend to be solid at room temperature. When we look at the other side of the spectrum, here, non-metals, these guys, not good conductors of heat and electricity. So, if you look at that, good examples, nitrogen is actually a gas at room temperature. Oxygen, gas at room temperature. Fluorine, same thing. Neon gas, argon gas, krypton gas. A lot of them are gases, so they're not going to be good conductors. They don't have any luster or shininess to them. You can't pound them out into sheets because at room temperature, a lot of them are gases. You do have like a liquid, which is bromine, but again, you're not going to be able to pound that out into sheets. Now, in the middle, you have the semi-metals. Now these, the conductivity is moderate. And the good thing about the semi-metals is we can actually control their conductivity. That's what you'll notice, a lot of electronics use semi-metals because you're able to control that conductivity. So a lot of metals, especially when people want to dispose of electronics, they say, make sure you recycle them. You know, a lot of them can have arsenic in it. Silicone is another element that's used a lot in electronics because you're able to control that conductivity. So because they fall in the middle, you're able to control that. And it's not going to be something where it's going to, you know, blow the circuit or not do anything at all. So they fall smack dab in the middle. So when you look at a periodic table, if I tell you to classify an element, you should be able to look at a periodic table and tell me, okay, carbon is considered what?
Non-metal.
A non-metal, yeah. Potassium is considered a metal, yeah. Periodic table will be provided to you. You don't need to like memorize it or anything. Just be able to look at a periodic table and know where the metals are, the non-metals, and the semi-metals. Then we can divide them up even more, classify them even further. Now here you have two colors. The first color is this yellow color. It's not as cute, but it's this yellow color. Now, if you look at a periodic table, you have periods and then groups. So you have periods, which are considered rows, and then groups, which are considered columns. Another name for this are families. Now, families, if we're talking about people, don't necessarily need to be related to each other. But you'll notice when families hang out, right, they have similar behaviors. Some are all complete opposites, like my sister and I, complete opposites. But you can have, you know, similarities to them. Usually when you think of a family, you think they're genetically somehow related, right? So when you look at this, the group number, one of the things you'll notice is the groups behave very similar to each other. The columns. And they actually have names to them, which we'll classify in the next slide. But you'll notice that these two columns here and the rest of them here are called main group elements. Now these main group elements are very predictable. The way they behave, their physical and chemical properties are very predictable. Then you have the guys in the center, in the blue. These are called transition metals. This also includes the elements down here, these guys here, because they're part of the transition metals. They're here. These are called a lot of times inner transition metals because they're right here. They just take them out. Now, these are not as predictable.